Hello everyone, welcome to our project presentation. I am Joshua and with me Lakshmi Narayanan Kaushal. We are final year BE student from Department of Electrical and Electronics Engineering at KLN College of Engineering. Our project is carried out under the guidance of Dr.S.M.Kannan, Professor and Head of the Department of EEE. Today I am going to present a project that addresses a very real and growing concern in the world of electric vehicle. The project is titled Dynamic On-Demand Energy Sharing for Electric Vehicles. The system is designed to allow the EV share its energy with another EV is need, creating a peer-to-peer energy support system. As electric vehicles became more popular, one of the biggest physiological barriers for users is fear of battery running out before reaching a charging station. This is what we can call range anxiety. Now, while EV charging infrastructure is expanding, it's still not mature or dense of fuel station. In rural areas, highways, or during long road trips, finding a charger in the time we can very challenging. At the same time, there are often electric vehicles nearby that have enough charge, just sitting idle or moving slowly with excess capacity. But right now, there is no system for vehicle-to-vehicle charging in on-demand, regulated and safe way.
Let's talk about how the system works and the components involved. The main idea is to control the sharing of DC power between two EVs in a safe, isolated, and controlled manner. The energy flowing must be carefully managed to avoid overloading or damaging the battery. We used components are microcontroller PIC16F, a reliable 8-bit controller with plenty of I/O pins and built-in timers. It acts as a brain of the system and control the logic for initiating and terminating energy sharing. The power supply we used are 4-volt battery with series in 12-volt battery, which we regulate using a 7805 voltage regulator. It brings the voltage down to say 5 volt for powering it, the microcontroller and the other low power controlled components. We used 11.059 MHz crystal oscillator for generating stable clock signal. Timing is essential in switching application and ensure consistent performance. We used the autocoupler force. It provides an electrical isolation between the control logic and the high power switching selection. When the controller sends a signal, the optocoupler activates and passes the signal to the gate of the MOSFET without allowing current to flow back to the controller. We used four MOSFETs, N-channel MOSFET IRF840 are used to control the actual current flow between vehicles. This acts as a switch that can handle high voltage and current efficiency. We used a capacitor and the inductors for voltage ripple and spike to reduce the currents. And the selector switch we used are in this prototype. We simulate the request for power sharing using a manual switch in a full-fledged system that can use to replace with a software controlled secure system using GSM, Bluetooth, or IoT platforms.
Here, let's see how the whole system working step by step. Initial status. Both vehicles are connected. The microcontroller remains idle waiting for the request to share the receiving power. Now let us see the trigger request. When the receiving vehicle sends the request using the switch, the whole process of the microcontroller processor which works with together in the system. Next, we can see the third step, which the signal can be initiated. The controller activates the optocoupler, which turn on the MOSFET switches. And next, the fourth step is controlling the power transfers. The MOSFET creates a controlled conductor path between the two batteries. The LC filter ensures smooth DC transfer when the power comes from the batteries. Next, we can see the fifth step, that is termination. The transfer can be terminated manually, automatically based on the current flow. And next, voltage threshold, which the timer can be controlled. The prototype safely simulates that controlled DC energy sharing in a simple circuit. When the vehicle plays the indoor road, both the circuits will work together, which receives the same power in between them, and which a bidirectional circuit, which it is a advanced technology.
Real-world use cases. Emergency EV rescue. On highways, if a vehicle is started, a nearby EV with enough power can assist, eliminating that need for their low truck or mobile charging van. Off-grid charging. In rural areas or during power cuts, this method can be temporarily bridge energy between vehicles. Smart urban network. In a smart cities, EVs can be dynamic modes, setting or consuming power based on need, time or day, or priority.
Let's see the future scopes and upgraders. The system designed to the modular and scalable. In the future, we can enhance it with wireless communication using GSM, Bluetooth, or LoRa, or sending power requests for another vehicles. IoT and cloud integration. Vehicle can automatically discover other nearby via GPS and send requests through a cloud platform for charging requests. Battery health monitoring. Integrate temperature SOC, set of charge and sensor to avoid unsafe transfer. We can even include payment or credit system to EV owner can get compensated when they share powers, similar to energy banking.
In conclusion, my project, Dynamic On-Demand Energy Sharing for Electric Vehicles, provide a practical, cost-effective solution for one of the most precious issues in the EV corporation. It combines microcontroller-based automation with the basic power electronics to deliver real-time support between the vehicles. If you have any doubt, queries, please comment below. Thank you.